Okay, so we're going to be doing lead code 450, delete node in a BST. So you're given a root node reference of a binary search tree and a key. The key is a value. So delete the node with a given key in the binary search tree and return the root node reference, right? So possibly an updated BST. So basically the deletion can be divided into two stages. Search for a node to remove. If the node is found, delete the node. So there are going to be four situations of deleting a node. If it's this node, right? So we're going to do a bottom-up DFS, right? This is a bottom-up DFS because you come down, you do depth first search, and say if it's 2 that you want, if 2 is the key, you find this node 2 at the leaf, you simply return none back to this root. So this node dot left becomes none, right? Then the other situation is if one of them is if both are empty right here where the key is, then you simply make this none, right? But then if one of them is empty, you simply return only the right side, only one side, right? But then there's the case of if it's a node with both sides, how do you delete a node with both sides? And the way you delete a node with both sides is to find the minimum node in the right side, because the minimum node in the right side will fit here perfectly, right? It will be, since it's a BST, it will be it will be larger than everything to the left, and it will be less than everything to the right. Okay, so that's why we pick the minimum node in the right side. So let's do the code and you see what I'm talking about. So we check if the root is empty, right? So if it's empty, then if not root, then we return none, right? Because it's empty. Then we check if we've found the key at this node. So we say if root, at every level is just going to be root, right? So if root dot val is equivalent to the key, then we have found a node to remove, right? And we have 4 things to do. The first one, if it's a leaf, we simply return none, right? 2 is if it's none on the left but has a right subtree, right? We return the right subtree to the root, right? And then 3, if it's none on the right but has a left subtree, we return the left subtree to the root, right? And then the 4th one is if it's not a leaf, i.e. it's a middle node, then we replace its value with the min value in the right subtree, and then use recursion to delete the node with the min value in the right subtree. And I'm going to show you how that's done. Otherwise, elif, we have not found it, but root.val will determine where we go in the subtree, right? So elif root.val is greater than key. It means that the key is in the left subtree, right? So what we do is we call self.delete node, right? Since this is recursive, self.delete node root.left and key. Else, that means root.val is greater than key, and so it's in the right subtree. So self.delete node root.right key, right? And then once we're done, right, but once we're done, we return this root, right? So once we recursively call whatever, we return this root back because we are doing bottom-up DFS. You have to return a certain value when you delete, right? And this is where we're going to do the deletions from here. Okay. So let's do this. So if it's so this is the case where we found the key, right? We found a node with a key. So this is the node we want to delete, right? So part one, if not root.left and not root.right, what do? We return none, right? Because that's the case where we are here at this node and trying to delete it because it's a leaf. We simply return none back here, right? And then part two is if it's none on the left. So if not root.left and root.right, then we simply return root.right. Okay. So that's all we're returning this. We're only returning this part, right? So if not root.right and root.left, we're simply returning root.left. Right? That's how we are deleting that node. And that's the, for example, if it was 6 falls in this 6, right? This 6 here falls in, and the key was 6 for this node. It falls in category 3, right? So if not root.right, oh sorry, that would be category 2. If not root.left, because here it's empty, but it has a root.right, we simply return this back into here, right? So that's what we've done here. Then the final part is if root.left and root.right. So that's this case, right? Where it has both sides. We delete this by finding the min value this side. Let's see if there's a better one. Okay, if it was 5, we'd find the min value this side, which is 6, and place it here, and then come through and delete the 6, right? So if root.left and root.right, okay, we're finding the min value. We do it by, we get a pointer which is equal to root.right. Right? We set our pointer to the right, and then we look through. So while pointer, right, pointer is equal to pointer dot left. So once it's done, our pointer is at the min value of the right subtree. So we set our root.val to pointer.val. That's how we delete it. All right, so we say root.val is equal to pointer.val. Right. Now we need to delete the value of the min node in the right subtree. And how do we do that? We simply return self dot delete node, but root dot right, and the key is going to be root dot val. So this should be it. Oh, root dot val is equal to pointer dot val. Root dot val. This looks fine. That means I made a mistake somewhere. Sorry, I should have written return here. That's supposed to return. Return root dot right. All right, we're just gonna check out this submission here to make sure. Return none, return root dot left, which is what I did. Return root dot right, while pointer dot left. Root dot right. Okay, so that was a mistake. This is supposed to be return root dot right is equal to, because you're updating the right node. So that was a mistake. Let's see if there's another one. Oh yeah. Here is supposed to return root dot left is equal to, and then root dot right is equal to. So this should work. Line 38, what's the problem? While if root dot left. Okay, maybe we don't need to, we don't really need this. So this should work. Invalid syntax. Root dot right. Root dot right, root dot val. Looks correct. Root dot val greater than key. It looks right. I can't see where I made the mistake. Return root dot right. Return root dot right. Return none. If not root, return none. That's correct. If root dot val is equal to key, that's correct. So where I have a syntax error. Oh, damn, never do stuff when you're tired. Okay, so it should work. Return syntax, return root dot right is equal to self root dot right, root dot val. This is weird. I don't know what's causing it. I need to check. If root dot val, if not root dot left and not root dot right, return none. If not root dot left and root dot right, Yeah, if not root dot right and root dot left, return root dot left. This is correct. Pointer is equal to root dot right. This is correct. While pointer. Oh, while pointer dot left. My bad. Yeah, while pointer dot left. Yeah. Okay, pointer is equal to pointer dot left. Root dot val is equal to root. Okay, you're not supposed to return here. And you're not supposed to return here. And you're not supposed to return here. Okay, so that means I didn't fully comprehend it. But basically, you're setting the root dot left, setting the root dot right. So this is perfect. This should work. Yeah, my bad. So yeah, anyways, that's the solution. I've kind of explained it. Yeah, so just make sure you don't make the mistakes I've made, and you should be good. The runtime complexity is O of n, and space complexity should be O of 1, right? Because you're just traversing this. Should be O of h. Space complexity is the call stack, so it's O of h should be O of h as well. So you can see here, space complexity is O of h. Time complexity is log n. Yeah. So that's the solution, and thank you. Bye.